Thank you. I think we are running 30 minutes late or more than that. So I shall try to 1 hour late. So I shall try to be brief because the foundation that has been kind of shared, foundation of the medical healthcare and AI, that part has already been shared by my previous speakers. So I don't need to emphasize any of those things. So what actually I would like to talk about again, something that has been kind of indicated, some low-hanging fruit. So ECG was one of the thing. Another thing that is there is the stethoscope sound. So the doctors in the audience, if there is any doctor, physician, doctor by training, no one. But otherwise, all of us know that when we go to a hospital or a medical center, so somebody will be having a stethoscope around his neck is the person who is the doctor. I mean that has become more of a distinguishing feature of a doctor. But how much of that stethoscope sound we are using? Like what Dr. Kunal Sharkar was telling, that 30% of the doctors can read ECG properly. So similar statistics is there with for stethoscope sound appreciation also. For cardiologists, people say around 80% of them can understand it properly. But for non-cardiologists, the stethoscope sound is not, I mean, less than 30% or 30% of that, that is the statistics. So what we thought that can we make, given that the advancement in signal processing, data acquisition that has taken place over the time, and of course use of learning. So that is the machine learning part of it. Now we are talking about AI, artificial intelligence. Can we all put them together to come up with something which is useful, much more useful? And so that is how the story started. That is the background. And our lab is audio and biosignal processing lab. We do a lot of stuffs in audio and speech processing. And of course, in biosignal also, we are looking at various things. And today my talk will be based on some of our experiences, more of case studies like regarding heart sound analysis. And before that, I would like to kind of tell one important thing is that there is a term called homeostasis. What is that? That when something happens, like one example has been there. So there is a change in blood pressure. So our body system tries to do things in a manner by which we can get the equilibrium. So there is always something happening within the body, and if we can appreciate that, then probably we are we can take a remedial action in a much easier and quicker manner than taking medicines, taking many other things that are people usually practice. So important is that whenever there is a imbalance is there, so you have to kind of understand that. So these body generated signals, so our philosophy, I mean, we all know that there is some indication, prior indications. So these indications that are there, if we can have an objective understanding, first of all, analysis, acquisition, and then analysis of this, so then it is easier for us to kind of take appropriate action following that. To understand this, then we have various methods. One is invasive, another is non-invasive. For invasive things, of course, there are problems associated with it. You have to have a trained person. You have to go to a specific place where all those invasive procedures can be taken up. So non-invasive is the way. But for non-invasive, then there are various aspects regarding what kind of reception system we shall have, right? Signal to noise ratio, noise aspect has been told a short while ago, and I was also discussing with Ognimitra and others that many things works in the lab. As soon as it goes out of the lab, it doesn't work. It goes to the field, it doesn't work. Why? Because of certain those noise that would be there from the system level, from the ambience, from various places, that would actually is not part of our laboratory study. So on field it doesn't work. So signal to noise ratio is very important. And of course the processing part of it, and processing, as I said, if we want to have a and not all the cases you need very big systems. So AI can be edge devices, IoT devices, those applications are there. And finally, the cost part of it is also very important. So that is where also our focus of attention ours would be. So compared to many other countries, India, you can see the number of doctors available per 10,000. This is the current stat that is there in the World WHO map. And this number was 6 in 2012 for India, and China was 15 in 2012. So currently the number has increased for India from 6 to 9.55, and for China it is 28.19. US and UK more or less remaining same. So regarding the sound appreciation, so if you look at the human audible range of sound, I have a pointer. So this is the hertz sound. So this is the hertz sound. So it has got this frequency versus the sound pressure intensity part of it. Okay, and this is the threshold of the audibility, and mostly the doctors are depending on listening to this. Okay, and the subliminal sound, or the sound that cannot be appreciated because of it is beyond the threshold of the audibility, over here this entire region is there. So you can have an appropriate acquisition system which can go past our individual physician's experience, and that also is becoming a dying art, as you have noted. So this is where we wanted to kind of look at. So initial our first level of study was on valvular disease detection. So the valvular diseases that are there, so our normal heart, if we all listen to the various movies, so lub dub, and they increase it depending on the situation to make it more serious and all. So that is the primary and secondary hertz sound, and in between there are systoles and diastole. So this is the usual operation of 4 chambers. 2 valves are opening and closing simultaneously in each of these cases. And when there is a stenosis or some such thing, so you can see over here, so there is an abnormal flow, and accordingly some murmur, some noise will be generated. And that murmur can be over the entire systole, so it's called pansystolic, over entire diastole or early systolic, and so many other varieties could be there. So our job was to appreciate that, which could be figured out by stethoscope. And this murmur has got various characteristics, and mostly these are of 2 types: stenosis, where there is a blockage happening, it's not closing properly. It is not opening properly, and regurgitation, there is a backflow, it is not closing properly. So because of this, various kind of issues could be there, and these are the places where different valves and the sound that is radially going out, those could be there. And these are different characteristics that could be associated with the murmur. So the signal processing or the pattern recognition, that job, that AI part related activity, actually would like to figure out this association, these features, the features that was told before. So in one of our traditional classification systems, so what we try to do, so basically whatever this heart sound is there, segment it, extract features, then create model. These are all from raw signal, large volume of raw signal, we are going into dimension reduction. So basically feature extraction is a low dimensional representation of this, where only the important informations are kept, significant information is kept. When finally model is prepared, again a lower dimensional representation of it. I am talking about the traditional classification framework. And then this model is stored, and when during the test phase something unknown sample comes, it goes to the same process. There is a matching algorithm, and accordingly it is figuring out whether it is a diseased case or a normal case. So these are some of the kind of activities regarding segmentation. So there are algorithms that has been developed. I mean, people then boundary estimations. This is told diastole, primary heart sound, secondary heart sound, and these are some feature extraction related associated with various diseases So these are acronym of those diseases. I am not going into the details of that. And this could be the 35-dimensional, say, feature vector. So that could be there. So similarly, these are different tools by which people can figure it out. And then these are some of the performance metrics that you can find out. And over here you can see for clean, the initial result that we are talking about was relatively good, very good. I mean 97% or so. But as Ugnimitra was telling, and many of the speakers have already pointed out, as the noise addition, this is the AWGN, but we have worked with hospital noise, many other kind of noise. So the performance deteriorates very drastically. And these are ANN with a single hidden layer. So around 32 hidden nodes were there. So then we wanted to carry out, see the improvement can be done when noise addition is, noise is still present, because field deployable is one of the important, requirement for us. So then we found some, database where there were some, reasonable amount of data, ground truth related things were present. So some 200 subjects for 4 major abnormalities, and this is normal heart sound, and this is normal heart sound. Of course, the breathing sound is associated with there. And then, so for this, 4 diseases, these are the characteristics of the heart sound, which we could figure it out. And then the 2-dimensional representations of this in the featured domain. These are name of some of those features not required for now. So this is some called spectrogram. This is called Mel spectrogram. It is widely used in the speech processing. This is scaleogram, wavelet, and some such decompositions that are there. And then these were fed as input to the model that I will tell later. But before that, this is how the noisy signal would look like, and usual bandpass filtering of the noise would result in what you see over there, which is pretty bad. Okay. And these are again some noisy signals for different kind of noise level, and for different kind of noise additions, so that you can see and understand the issue of noise affecting the signal and the treatment that is required. And for this study, the result that I will show, this we have used a method called transfer learning, in which a big model with very large number of parameters, etc., was trained on audio signals, which has been taken from YouTube. There are a large number of 521 classes that were present. Okay. And the number of parameters and other things are quite huge. Okay. As Professor Shomo just now told. Okay. But it was trained, this pre-trained model was used, and a method called transfer learning, where further fine-tuning was done with the heart sound data. And then this is the results for clean signal. And of course, we used other pre-trained model also. I mean, this one we got best, so that's why we presented there, but others were also equal, reasonably good. And then we did that noise study, and we found that with noise study, the result was so less, for the other model, the shallow model that we had seen there, which is reasonably, good, above, 90%, 93% or so. And these are some of the systems that we have developed, patented, transferred to company who are now conducting, hospital trial of their version of the product that they have come up with. And these are some of the, the system level, descriptions. And I'll stop here because this was single channel. Then we went to multiple channel. This is the company made version of the hardware. This is the 4-channel multi-channel versions. So to move beyond, and the CAD was talked about by Dr. Kunal Sharkar. So basically, this study was done on CAD disease, that is coronary artery disease, and we had significant result on that. But I think the time that was given, I thought that only one part we can take up. And of course, though we are talking about healthcare, and we wish that all remain happy, and we don't need to have all these things. But life is like that, and we have to kind of live with the reality that it may fail. But if we detect early and if we detect in time, we can take remedial action. Thank you.